Section 3.8 is called kinetic energy of linear motion. We're going to look at an equation 3.7 that is going to quantify the energy contained in something that is exhibiting linear motion or motion in a straight line. The equation for that is given here, where energy with a little subscript K for kinetic is equal to 1/2 times the mass times the velocity squared. And if you've had a physics course or other, you may have run across that before. The kinetic energy will be measured in joules, and the mass, of course, in SI units would be in kilograms, right? This would be kilograms. And here we go with some of these disconnects. You know, we talked about, when we talked about the power of a motor and we multiply the rotational speed times the torque divided by 9.55, the speed was given in RPMs. Here we're talking about meters per second. So it's in strictly these SI units. So, you know, always, you know, create these formula sheets and make sure that you are clear with, you know, what units are used in what, you know, in a specific equation. And, you know, you want to write that down. You know, if I'm making a formula sheet, just writing this equation down is not enough. You know, I need to describe the components. Mass is kilograms and velocity is in meters per second, and the energy kinetic is in joules. So you always want to give the types of units that are used in the particular equation. So anyway, a falling stone, a moving automobile, they all have energy due to motion. Something in motion has energy. We can harness that energy and do useful work. Kinetic energy is a form of mechanical energy, and he gives us an example, and we'll work through this, this example here. He says, I have a bus, so let's see if we can imagine a bus. I'll do my best bus. Sorry, that is my best bus, okay? So here's a bus, and this bus has a mass of 6,000 kilograms. This is example 3.8. And it is moving at 100 kilometers per hour. It's about 60 miles an hour, right? 100 kilometers per hour. The bus is here, and so we've got, he says we've got 40 passengers, and they have a total mass of 2,400 kilograms. So the total mass of this passenger plus bus is 6,000 kilograms plus 2,400 kilograms, or 8,400 kilograms. Calculate the total kinetic energy of this loaded bus. Okay, well, I can do that if I do some conversions. This is a bit of a problem, and I got to take care of this, okay? This 100 kilometers per hour. I need to convert that into meters per second. So what does that look like? You know, what does that conversion look like to be able to convert, you know, that to meters per second so we can use it in our equation? So what that looks like is here, where we've got 100 kilometers per hour and we want to convert it to meters per second. So we have to convert the hours to seconds, and we have to convert the kilometers to meters. So let's take care of the kilometers first. We know that 1 kilometer has 1,000 meters, so these are going to cancel out. We know that 1 hour here and here has 1 hour, that equivalence there is 60 minutes. So the hours cancel out here. And we also know that 1 minute has 60 seconds. So the minutes cancel out here. What are we left with? We're left with seconds. and we're left with meters. Okay, so we go through and we do that calculation, and we come through, we multiply 100 times 1,000, divide it by 60 times 60, which is 3,600, and we're going to come up with 27.8 meters per second. Now we have the values in the form that we need them to be in, that we can use in our equation 3.7 up here. So let's take what we have and let's put that in this equation, where the kinetic energy is equal to 1/2 the mass of 8,400 kilograms times this velocity, 27.8 meters per second squared. Okay, now we run that through our calculator. Of course, you want to do this first, then you want to multiply that, then take half of that, and ultimately you will come out with 3,245,928 joules of energy, kinetic energy, that is contained in this moving bus with these 40 persons on it. And then a better way to write that, we want to write this as 3.25 megajoules. Okay, so this moving bus has 3.25 megajoules of energy. Now I want you to think about this, that there's an energy of linear motion, you know, it's moving forward. And for us to stop this bus, you know, we apply the brakes, and to get this bus to come to a complete stop, we must apply frictional heat, you know, to this. We must convert this kinetic energy into heat energy. And when we convert 3.2 megajoules of the kinetic energy, and we convert that to heat, and it's dissipated as heat, then this bus will come to a stop. And, you know, that's another energy conversion process. And then, you know, that's representative of this particular problem.